Okay, as I told you before, we will start now with an introduction, a very short introduction on introduction to trigonometric functions, which is basically another possible family of regressors. In order to understand that not only trigonometry, not only polynomial can be used, but also basically any kind of functions, or as I told you last time, combinations of functions, no? Not necessarily basis, but forget this word basis because this is more mathematical concept. Yeah, and the idea of today is again to reconsider how we can choose between families, because until now we have seen just one family, but do you remember I told you the concept of the number of coefficients? Now we will reconsider this criterion, and yeah, during I will discuss during the presentation of this family. Let me open the presentation, which you will find also today in my study. Let me share. I will consider just a part of this presentation, just a part of this presentation. We can see 22. This means it's just background. But I will skip most of these slides. But let me start introducing this new functions. Let me say trigonometric basis or trigonometric functions, or Fourier functions or Fourier basis. Probably the engineer know about the Fourier. But anyway, some questions, or these questions are exactly the same. At least let me. Okay, now we can see. Do you remember how to choose appropriate functions for approximating curves? As the questions with which we started the course in which we during the course I try to open the most important issues. Also, which one? In any case, I don't want to repeat again, but the most important concept we already discussed. The introduction of a cost function, R square adjusted until now. But of course, we have also different cost functions. Believe me, it's not the unique one. Is, in my opinion, one the most important. Therefore, I spend energy just on this. But believe me, the cost functions can be chosen also in different forms. How this, if we go together through the project, we will see. It could be that we can consider also different functions, but anyway, considering specific projects. In any case, we have a cost function. Fourier, or trigonometric functions. Look at this proposition. Fourier is the mathematician. Each periodical function can be approximated through summations or summation of sine and cosine functions. Each periodical function. If it's not, we will see that we can do nevertheless. But of course, we have to pay the price. Yeah. In our case, we don't have exactly a function to be approximated, but we have data. We have a point of possible model, which is a function. It's not so particularly different, but in any case, we have to adapt. You have to adapt this proposition at our specific problem, and in particular, typically, we don't have periodical function in the sense of periodical data because we have a limited number of data. Now I will show you later what is the meaning of periodical function. No? This means we have a mathematical expression in order to be clear, but this means after t, let me consider periodical in time. After t time, I will repeat every value which I have before. But of course, this means mathematically for a horizon of time infinite. Otherwise, it could happen that some when is not theoretical anymore. This means the theorem or the proposition which is written here is in a theoretical expression, but it's or sentence. Of course, is an expression which came from a mathematician. Now we will see how we can adapt in our case. Forget the last part of the or in particular, the bottom part. Let me consider just this part in the frame. Why that? Because we discuss a lot, 4 lectures about the Taylor functions, the basis. You remember this? We know now. I am boring if I repeat again what is this approximating expression. Isn't a sum? It's a shame I didn't put here, but try to image. Y hat indicates the approximating function equals sum of what? K starting from 1 up to n of what? A k, which multiply x up to k, right? In this case, I would like to consider, if I consider k starting from 1, yeah, it's a little bit strange with respect to this one. Yeah, I didn't put because it's not exactly what I told you. But believe me, we can write. It is easy to think, but it's wrong what I told you now. Is we can write this in the form of sum. It's in sum. Let me see. Yeah, could be from k starting from 0 up to n of a of k x up to n minus k. Now it's correct. I will get all elements here. All elements here. Isn't a sum like this one. This is the trigonometric function or the functions which we consider as a regress. We consider as a constant. A0 divided 0. Here the constants an. In some books you can find here an x up to n plus and so on. An minus 1 x up to n minus 1. We can see different possible notation in some books, but in any way, isn't a sum, clear. Here, nevertheless, isn't a sum, but we can see that historically or that typically we have this constant outside of the sum plus the sum of sine and cosine function. K is basically represent somehow the number. Why not the number of elements which we are considering in the regressor, and in particular, if you look here, K dimensionally from the dimension is T. Now we will see what T is. T could be represented the period, for instance, the period in time, but not necessarily in time. Could be everything divided x. Divided x. In any case, K states the number or the index which allows also to state the number of functions which we have because it's running up to n. It's basically the index of the sum which we have here up to n, if you want. Of course, in a combination of sine and cosine, for different reasons, for different mathematical reasons, which I don't want now to let me say to clarify because it's a little bit outside of our goal. But anyway, let me consider this possible function to approximate points, to approximate measurement from a process, excuse me. We can see that the coefficients which we have here, the coefficient p, do you remember we call the number of coefficient p, we can consider here equals 2n, we can see as 1n is here, 1n is here, element, plus 1. Here we have a p, do you remember, equal n plus 1. But this does not mean that the coefficients which we used here is more than this one. Even though it seems to be 2n plus 1 larger than n, mathematically, yes, but please consider that we have to approximate the points. This means I don't know how many elements I need here and how many elements I need here. I will clarify now a little bit better. If you consider, for instance, data, periodical data, exactly as I told you before. If I have a periodical data, even though it's a limited interval of time, the coefficient which I need to approximate the periodical data here with the same error, R square adjusted, for instance, which we have here, typically is less in this case here because this structure is suitable for data which are periodical somehow. The period is T. Must be known, could be known, but if it is not known, yeah, we can estimate. Basically, here to estimate are A0, BK, AK, and eventually T. But if T is to be estimated, we have a not convex optimization problem. Now, let me go in depth on this aspect, which I already told you. Forget everything here, forget everything here, because this is a lecture for engineer, in order to demonstrate why sine, cosine, and different things. Forget this. Let me go at the end, in which my idea here in this course is to compare, again, the two approaches, polynomial approach and the trigonometric one. Again, this expression and this expression are the same, which I try to introduce now, exactly now. This expression here, I don't need now to repeat, because I think I repeated many times. But I put everything in the slide in order to compare, in order to understand the difference and to go in depth what I told until now. Look, just roughly speaking, this structure here, it looks like this one. For instance, of course, the measure that I have the same, because I have the same phenomenon or the same phenomena, which I want to approximate once with trigonometric function. And another one, or then to compare with the trigonometric ones of trigonometric function. This vector, these two vectors are the same, the data. Circa, I clarify many times why the meaning of circa. Look at this part here. This part here, as here, are exactly the parameters which I want to estimate, which I need to estimate to perform, to calculate my regression. In this case, you remember, many times I already told you we have A0, A1 until AN. Here is a little bit different because if you look at this structure here, we have A0, which is here, B1, A1 until Bn, An. If n is also in this case, I would like to say the number of the trigonometric functions. Really, the trigonometric function is 2n because n for sine and n for cosine. I don't know if you remember sine, cosine a little bit. Yeah, here in the middle, and then I will go in depth on this. Let me say in the middle, in this exploration matrix, we have in both cases the exploration matrix. Where this matrix comes from, I will go now a little bit in depth, but let me discuss, roughly speaking, this exploration matrix. You remember here, I told you if n is unknown, we have seen last time. If n is something which I have to calculate, if I have to optimize, you remember last time I insisted on the optimization of n. How many elements in the Taylor series or in the polynomial, or how many polynomial elements, let me say so, I need. The problem is not convex. The optimization problem is not convex. Therefore, you remember last time I told you how we can heuristically. I try with this, I try with the method of trial and error. Now we will, if possible, also today, we will start also with a method, a systematic method. The name is PSO, particle swarm optimization method, which can be used to attack not convex optimization problem, avoiding a part of this heuristic method or heuristic form. Here, again, n is also there. This means if n must be optimized, also here, we cannot divide it, what I know with what I don't know. Remember this concept here. In the exploration matrix, we need to have everything known in order to apply exactly the least square. The least square means that theta equals parentheses x transpose multiply x inverse multiply x transpose multiply y. Should I come back? No, I told you a lot. Here we have another parameter which must be optimized if I don't know. T, the period of the data, the period of my hypothetical, let me say, regressor or approximating function. Let me go in depth how I can build this. And then I hope to relax a little bit the lecture, not immediately. I would like to tell you some possible problems, and then we will look in MATLAB a little bit. Because now it is extremely important to understand the difference in between. And in any case, it is important to emphasize this not convex optimization problem, because the next topic is PSO, particle swarm optimization method, which is a solver to solve, to find minimum or maximum, an optimal point of not convex optimization problem. Look, don't be scared. I already told you that time. Yes, no? I think this slide I have just two heavy slides, and then 1 second. And then everything will be a little bit easy with MATLAB, I hope. Look at this. Now we know the regresso in this form. T can be chosen. Or if I cannot choose, if I cannot see in advance, if I cannot choose this in advance, I have to consider an optimization problem. Again, the problem becomes not, the optimization problem becomes not convex one. Look, it seems to be complex, but it's not. I am considering the first point, exactly as I told you at that time when I introduced the polynomial approximation. Y1 is circa y hat at x1. Do you remember the difference between the point and the point with lies and the blue function? But now, in our, or consider this expression here, is A0 divided 2, because does not depend of k. Also, in Taylor, we can consider the k. It could be that I will improve the slides also to show you more clearly this parallel form. Because also there I have a sum of elements. This means can be expressed in the same form or a similar form. Why this? Because I am considering this element here at, let me say, k equal 1 is not explicit at point x1. I calculate basically this expression here at point x1, starting from k equal 1, go ahead k equal 2 until k equal n. This means I have this element here, which is here for k equal 1 at point x1. Let me consider t is given. I know t, the period of the data. Again, to be concrete, I don't have to say much time to go in depth on this, but as you see, I skipped every theoretical part because it's not the goal of this course. but we have to be able to apply. I do the same at the point x1, but considering k equal to for sine and for cosine. Basically, it's exactly what I do, or what I did for the form of Taylor when I introduced the approximation using the polynomial or the Taylor base. I will go ahead until k equal n. But in this line, we have the calculation of the regressor, the general regression, at point x1. Basically, this is the difference. If you consider y1 minus y hat x1 is the difference between the points and the possible and hypothetical point on the regressor, which must be calculated using the least square. If t is given, and of course n is given, is exactly as I told you at the beginning of the course from considering Taylor. N is given, t is given. I will calculate abstractly. What is the meaning abstract? Because I don't know A0, I don't know B1, I don't know A1. Must be calculated. But I can do that directly with the method which I told you with the Taylor. Yes, because the problem is convex, because I can consider the same cost function to be optimized, the least squared, and I can, in the constraints, in the representation, I have basically what I know and what I know totally split. I do the same for x2. This means I am considering this expression here, calculated at x2. The key point is I am considering this expression here for a given t, for a given n, very important. Otherwise, I cannot separate what I know with what I don't know. At point x2, and I have this expression. I do the same until the point ym. It is clear. It's exactly what I did for the Taylor or the polynomial function. But of course, here we have to consider another structure of the regressor. Please pay attention. I can mix also polynomial and trigonometric function. I can mix. Believe me, you can do whatever you want. But of course, if you mix, we end up in a non-convex optimization problem. Believe me, I don't have time to show you this, but it's clear from the concept that you cannot separate what you know with respect to what you don't know, typically. And then, of course, it could be that it is possible, but in general, no. Okay, look, now, how I can obtain this formula, which is exactly what I told you before. Yeah, this element here is vectorialized in this column. The element which must be calculated, this means A0, B1, A1, B2, A2, everything which I have in each line is vectorialized as I did for the polynomial in this column here. And then, now, we know the game, let me say, row multiply column should get this expression here. I mean, this representation, mathematical representation in terms of equation, is exactly the same in terms of matrices and vector. The advantage here we have seen with MATLAB, that MATLAB, any kind of programs, any microcontroller can work very well with tables, matrix and vector. With this language here, is a little bit more difficult, because we organize everything in tables, which, assuming that I know T and I know N, everything is in the exploration matrix known. This is unknown, this is known, and in this sense, I can apply the equation which I demonstrated. I didn't do the calculation, but I showed you, I sketched a little bit the calculations, can solve the unique point. The unique point is characterized by these coordinates, A0, B1, A1, and so on, theta point, or the theta vector, if you like. The vector isn't a point. I don't know if you remember in high school. I don't know. If you do, this row multiply this column, look, we will obtain this expression, which means U2 is equal this expression, oh, at circ equal this expression. Look, 1 divided to A0. Then we have B1, which multiply, because it's here, no? This multiply this, and this is exactly this element here. Let me show you better. Okay. I had something to write, but I'm fine. It is probably in order to indicate. No? You remember the rule row multiply column, easy, no? From math. This multiply this is this element here. This plus, no? This multiply this is this element here. This multiply this is this element here, and so on. You can do that for all row of this matrix. Now, the trick is once we have this matrix here, is the matrix as before, exploration matrix. Basically, roughly speaking, the problem is already solved as before, no? Because we can apply the expression to calculate. Let me see the vector theta, which consists now of 2n plus 1 element. This does not mean that the element is larger, the number of elements which you have in a trigonometric function is larger than the polynomial. That depends on the data. Because really, if the data are periodic, we need a few parameters here, really, a few parameters to fit with the same R square adjusted. And this is a criterion which can be used also to choose between polynomial, trigonometric, between any kind of regressor which we can consider or which we can build. We can also mix families. I don't know if you remember last time, in which the criteria was basically at the end the number of coefficients. The minimal number of coefficients which realize the minimal square adjusted is our ideal, or our regressor which we consider as an optimal regressor. In this sense, we can choose also between two possible families, which is the best. The minimal square adjusted with the minimal number of coefficients. Of course, it could happen that sometimes we have the minimal square adjusted, but the number of coefficients is larger. This means we have a problem not easy to be solved. This means we have to look what is the difference between the both square adjusted and the difference between the number of coefficients. Typically, in engineer fields, the number of coefficients, the minimal number of coefficients is priority because we have to apply this approximation inside online, I would like to say, and inside a very short calculation time. But anyway, this can be done together, if we consider some project in this topic through when we will work together together with your specific project. Let me open MATLAB before showing the last heavy or boring slide in order to show you this typical problem which can appear using the trigonometric functions. Probably before opening MATLAB should be nice if I open another slide, another presentation, because otherwise it could be that is too abstract. Or I hope that with this slide, we can understand better. Let me see. Let me share. Two words about let me show you just this slide. Then my idea is to open MATLAB practically, and then show you something more practical. And then I will try to interpret what happens in the MATLAB simulation. I hope that I share this. Yeah. Look at this slide. Of course, also in this lecture, I skipped many slides. This is. I don't know if you heard about the Shannon theorem. It's not. I am not here to tell you in detail this. But look at the picture, practical. Look at the picture here. We have here, for instance, 4 measurements. We can see here, no? 1, 2, 3, 4 measurements. Of course, here is not an approximation because it seems to be that the blue line and the red line both meet the points. The problem is this one. It's not a problem of approximation, of course. It's a problem of the reconstruction. I mean, if I have this, it seems from this picture, if I have these 4 points, it seems that it could happen that for these 4 points, we have a more than one line. This is not, it's not something which is totally, we are not surprised in a sense. Because if you remember in the polynomial, if I have 2 points, I can meet both with a line, but I can meet both with a parabola. I don't remember in high school. Any regressor with the order with n larger or equal 1 meet all points. But here the problem is a little bit more complex because it's not related to the order, but is related, we can see here, to t. This means if t, this period which I introduced in the regressors, is less or equal 2 times multiply ts, which is the distance between 2 measurements, we have such kind of problem. Or we can have such kind of problem. This means in a sufficient condition, in order to avoid this kind of problem, it's not a problem of the approximation, but we will reflect this problem in the approximation. I will show you now with the MATLAB, without going depth on the theoretical part. If this condition is guaranteed, now we can say that this problem here in the reconstruction of does not appear. Otherwise, we are not sure if I can meet all points with the red of the blue line. It could happen that I have 2 possible, let me say, solutions. Now, also in the approximation, this aspect must be considered because otherwise we will see that we'll end up in some singularity in which the problem cannot be solved using my equation. Why that? Because the equation will find one solution. Of course, in the context of the approximation. This means we can consider also here, in this case, I directly consider the Shannon theorem, but also if I am consider the approximation, the problem is this mathematical expression cannot work. Cannot work. We will obtain some singular solutions or some solution which are not totally acceptable in this sense. Let me now explain a little bit in the practical form this theorem, which I don't have time to demonstrate, but I will like to show you some possible problems. I will show you not only the problem of Shannon theorem, also another aspect related to T. Here is more important, is extremely important because T is a parameter which must be known or must be optimized. And a sufficient condition, but not necessary, is this one. That T should be large enough with respect to the distance of the measurements, x1, x2, x3. But the problem is, what happens if the distance is not the same? Yeah, in this case, we will consider a more conservative condition, which we will consider the maximal TS. But of course, conservative means in order to be sure that we will work. I will come back with the simile MATLAB on this problem here. Here is represented exactly to meet the points, but of course, the same problem will appear. We have the same problem if I have to approximate, because do you remember we have a unique solution in the context of the not in the context of the convex optimization problem, and if T in this case is constrained in this form here. Okay, I think I didn't forget anything. Let me repeat this together with another possible problem which we have for T, for the choice of T. Do you remember I told you at the beginning, T must be chosen. I click on the MATLAB. Let me share. One second. I don't know if it's the risk that I open MATLAB 2 or 3 times. This is. Yeah, no. Oh, yeah. Right. Just a second. I am opening MATLAB. Do you see MATLAB? Yeah, here. I hope that I share. Okay. Let me open, I think, this one. Let me see if it's really this one. I'm opening this. MATLAB. Probably it's not this, but we can work also. I think I click, but it's not open. Huh? Okay. Well, let me see. This one. Let me one of them. Let me start with this. Look, you know this file. Huh? I mean, the structure of this file. Clear all, close all. This is the exploration vector. This is the measurement. To 1, we have 10, to 1,5, we have 14, and so on. Look, t equal 4. Let me consider a little bit larger at the beginning. It's given. Again, we will see that if I don't give t, we already told you we have a non-convex optimization problem. We have to proceed in a different form. T is given, and look at the matrix here. N is also given, because we can see that we have just k equal 1, we can see here, and k equal 2. This is k equal 2 for sine. This is k equal 2 for cosine. This means it's fixed. We are in the context of a convex optimization problem. In fact, look, this is the solution. This is possible. Now, it's possible because, as I told you, the problem is convex. But the analysis, what I would like to do now, is the problem of t. Because t is in a parameter in accordance with the Shannon theory, should be chosen in particular form. Not only, for another reason, we will see that could be also critical. Do you remember the concept each periodical function? Now we will discuss also this hypothesis. All possible hypotheses must be discussed, because here we are not exactly in mathematics. Here we apply. This means approximation, hypothesis which is not valid, when is valid, or how can be considered valid, which condition can be considered valid. Okay, the rest we know everything. This is already our solution. This is exactly the regressor which I have considering just k equal 2. I don't know if you remember last time this expression here as a function of xs dot each element of xs, which is basically a new vector in the domain between 0 and 10, in order to visualize the solution. I mean, the solution is already here. Is already here. Here is more important the visualization, because we will see sometimes to have a feedback. What happens with respect to t is extremely important. Now I will clarify what intent. The rest we know. Here also we have R square. If you want to do R square adjusted, you remember we have to multiply here m minus 1. Do you remember? M in this case minus parenthesis p plus 1 parenthesis. Anyway, copy exactly the coefficient of last time, no? R square adjusted. In order to compare, if you want to compare in your project, if we need to compare the trigonometric with the polynomial one. Let me look what happens. T, as I told you at the beginning, is the period of our regression. But look, if you look at this data here, 10, 14, 15, 20, 17, 14, I don't see any period. I mean, now we'll try to introduce the last difficult slide. What is a periodic function? or in our case, when the data are periodical. Probably you remember it from high school or from math. Look, periodical function, let's think if you want, in our case, periodical data. But this is exactly the definition of a periodical function. F of x equals f of x plus t, in which t is the period. This means after t, I will reobtain the value as before. Basically, this value here is repeated at t, and so on, until infinite. This, of course, is a mathematical definition because we don't have infinite data, but very often they are really, it depends of the data, of course, depends of the process. Why I am telling you about the periodical function? Because sometimes in the phenomena, we have periodical data. We did with a student in political science, in a prediction of the election, using this trigonometry function, because we realize in the data and a periodicity. If you want, we can restart, also reopen this project. And of course, if you want to work with political element or issues or problems, elections, no problem, election. Now, in our case, look, coming back. We don't. It seems that we don't have any periodicity here. This means if you consider t large enough, large with respect to the domain in our problem is represented by the x, the inspection data. If I put a relative large t, look what happens. You calculate a square adjusted. I hope it's running, huh? Yeah. Look. Nevertheless, look, inside my domain between 0 and 10, exactly 0 and 9, we can see that the approximation is not so bad. Because we assume that the data will be periodic somewhere. This means in the domain, we can accept this because we can assume that will be periodic somewhere. I show you what I intend. Let me plot now the data. Let me plot here the data a little bit larger. At least let me consider 2 periods. The period is 20. Let me consider 40. This is our, let me say, domain or exploration domain. The word, exactly what is exploration. Now, I am assuming that we have a periodicity starting from 20, far away from my exploration domain. This means in the domain, we don't see this periodicity. This is the inspiration idea. Look what happens. Why this working nevertheless? If t is large enough, because I am assuming that the data are periodical, because otherwise I cannot use this system here. But you can see that I will repeat the data starting from 10. But inside my domain, they're not periodical. This means we can use this method even though the data in the domain on the Uh, yeah, like why not domain? Probably is better than exploration domain. Anyway, we understand what we intend, uh, and not periodical, because here the periodicity is not visible because the periodicity is, we assume to be far away from the exploration domain. Of course, this way to represent, if you calculate the R square adjusted with respect to polynomial, is not a very suitable function, could not be very suitable, because to obtain the same R square adjusted, we need, it could be that we need more elements, more elements. But anyway, not necessary. No, it's not necessary what I'll say. Because here, for instance, try to do atom. No? Here, for instance, we have four elements. Basically, we have 5 coefficients, right? We have this element 2 and 4 trigonometric elements, plus 1, 5 coefficients. And 5 coefficients means for us the polynomial order 4. Try to compare with the square adjusted what happens with the polynomial order 4. And look, of course, are optically, but very important, are square adjusted. I don't know, this could be a good exercise. Now, question. I will improve if I increase t. Yeah, try to do at home. It could be that will improve, but you cannot put infinite or that very large elements. The reason is, I don't know if it's this now as an exaggeration. Because it could be that we have an improvement increasing, but look, this is no meaning, no sense, because a square cannot be negative, because a square is a positive value, therefore square. The reason is that this matrix, if you look at this t in the denominator, becomes singular. I mean, t very large, this value here tend to 0, this value here tend to 0, this means sine of 0 is 0, this means we have a column almost 0, this means numerically will be singular. Now, Shannon theorem. Let me see what happens if t is not large enough. You remember, we need t larger than 2 times ts. Let me see 4. Oh, look, strange. Same problem. Not only. Of course, also graphically, we can see that the regressor is quite strong, because here we have our, let me say, real data, and then it seems to be between the first and the second one. Let me see a little bit better. Yeah, between the first and the second one, it is almost 10, 12, 14, and the possible approximation is minus 500. Of course, it seems to be strange, but this is just optically. Look at R square, something which is that does not work. Let me analyze why. Excuse me. In order to analyze why, let me come back to the theoretical aspects. Theoretical, but just the last. As I told you in the example, I am considering k equal 1 and k equal 2. Do you remember? Just sine cosine for k equal 1 and sine cosine for k equal 2. Exactly in the matrix. Do you remember? I told you we have just 4 trigonometric functions. Exactly what I am telling you here, consider just sine in order to understand. We have a blue sine characterized by k equal 2, and we have a red sine characterized by k equal 1. You can do the same concept, the same idea, the same analysis for cosine, but I put just one to be a little bit more clear. Do you remember in math, the sum of two periodical functions are again a periodical function? If, of course, the period is the same. Or if the period is an integer value, I mean, we can see we have a two period. One is t and one is 2t if you want. No? I don't know if it's visible. The red is t and the blue is t divided 2, right? The difference between, let me say, the ratio is basically 2 or 1 divided 2, depends. In an integer ratio. I mean, again, the period of the red is t. The period of the blue is t divided 2. This means the ratio is 2 or the 1 divided 2, depends. In this case, we can say that the sum of these two periodical functions, again a periodical function, because the ratio is an integer value. A little bit too math, but let me finish in this sense here, to conclude here. Look, what say in this case the Shannon theorem? The Shannon theorem says that t, in this case, must be 4 times larger than ts, in which, in our case, ts, we can see here, is, or the better, I would like to, I would like to consider it in this form here. T, why this is conservative? Because I am considering the shortest. You remember, the theorem, the Shannon theorem says something like that. Ts less than t divided 2 or t larger than 2 multiplied ts. We have seen both, no, in the slide. Now, this expression here in our case is the most conservative because I am considering the shortest period, because we have a two possible period. If this is guaranteed, this means t larger than 4ts, I am sure it is enough to say that I have a unique solution and we don't have singularity, because I am considering the fastest harmonic which I have. Because if this is basically guarantees for the blue, it's also guaranteed for the red. Because t larger than 4 times ts is valid also for t larger than 2 times ts. Now, let me show you in our case. Okay, 4 times ts. What is ts here? I have to consider the larger ts. Here is 0,5. Here is 3,5. No, excuse me. uh, 2,5, right? No, 3,5. Here is 2. Yeah, this means I can consider also, let me say, 4 times. No, 2,5, right? No. Yeah. The larger TS is here, no? Because the distance here is 1. The distance here is 1. The distance here is 1. The distance here is 2,5, right? No, 3,5, what did they say? Oh, stupid. See here the results. Yeah. Still okay, but decreasing. Excuse me. Decreasing and decreasing. Let me show you again. Can occur some problems. For instance, so, opla. You sure? Yeah. Let me show what happens. Look, of course, here we can have some doubts that the approximations becomes a little bit strange because between this point here and this point here, it seems to be that the regresso propose minus 16. So of course, and R square is basically is a value which does not explain exactly what happens here, because here in the let me share. Yeah, again. I mean, explain in the sense that we have to be careful because R squared without square adjusted something which is related to just SSE. But of course, in order to minimize, in this case, we are not minimizing SSE, we are maximizing SSE. Do you remember? R squared to very few values minimizes SSE. This means we realize that we have something strange in the approximations. This is due to this Shannon aspect, which is not guaranteed. Let me show you a little bit, a few words, and then we will conclude. Also with this, no? For instance, should be a little bit better, but not much better, but a little bit better, because here we violated Shannon, but not much. No? Please pay attention. Shannon is an enough condition, not necessary. But reducing, we can see that, remember, the limit was 3,5. No, I am stupid. What is the difference between 5 and 1,5? 2,5. 2,5. Right? The difference between 5, I'm concluding, 5 and 1,5. 3,5. Oh, again, with 3, we start to have some problems. No? Oh, not yet, we will see, but reducing, we had some, this is acceptable. The reason is, this is conservative. This is in a conservative situation. 3,5 is the conservative situation. It could work also with less t, less than. I try to clarify again before concluding. 3,5 is in a conservative. This means in this case, better to say strictly large than this will work in any case. Our unique solution, our unique. But of course, it's conservative because I am considering the fastest harmonic. This means, of course, can work also less than 3,6. But we have seen this, for instance, that we start to have some problems here. No? That was. Yeah. This was, of course. Now, it's not really acceptable, this, what we can consider not really acceptable, because probably, yes, I don't know if really we violate the Shannon, but in any case, we are close to the condition. The condition exactly must be calculated. Now I calculated just in a conservative form, as if I have the fastest, just the fastest let me say, harmonic in the signal. We have 2 harmonics. This means it could be necessary the fastest is violated, but the slowest, no. This means it seems to be work somehow, even though you have some doubts. But of course, reducing, as I told you, let me conclude with this. We have necessary some problems. Here, for instance, with 2, we have seen that probably in this case, we violated both. No? No. Yeah, very close to 0. And the result is this one, which clearly we cannot be considered a good value, in a sense, good approximation. Okay, next week, we start with the particle swarm optimization method. We will see that the method allows to find solution in which inside and non-convex optimization problems, such this one, in which t must be defined as an optimal value. I mean, we have seen t too large, we have numerical problems. T too small, we risk, I would like to conclude it, to violate the Shannon condition or the Shannon theorem, which is enough condition. This means we can violate. But of course, in my opinion, we have seen also today, if Shannon is not guarantees, we have some, probably could be, we can work, but the approximation is not so optimal because roughly speaking, we have a few data inside in the period. Or inside the domain which we want to consider. Okay, let me conclude here. Next week, a very important topic, PSO, because we will go in depth on not convex optimization problems. And in particular, I try to explain some basic knowledge related to programming, I would like to say, if, while, a for loop, because I will clarify PSO structure built directly by myself, but came from a project which I conducted, which I did when I was in ABB Research Center in Heidelberg. If you have questions, we can stay here to discuss. Otherwise, next week I hope to be a little bit. I think next week I don't have a meeting. This means I will be here a little bit earlier, I hope. Thank you for your attention. We will see next week. I will upload all this material in my study.